the Institute of Acoustics in Rome, and I'm going to introduce his theory about the sea urchin model of the electropotential, and then I'm going to show you how it relates to climate more in a later presentation. And I'll try to get through this quick. I won't belabor every detail.
Can you change yours?
I can do that. All right. I'm good. Okay. And thanks for inviting me to the NPA. This is my first NPA conference. I live near Denver now, and been working on climate change ideas since '95 when I first put a surge tectonic idea. If anybody's ever heard of surge tectonics, but let me just go through this as quickly as possible. We're on time crunch. So we're going to discuss these 5 items in both presentations. The internal and external way is, I'll explain that in a minute. Endogenous energy generation. This is Giovanni's ideas, and I'm sure there's other people that have similar ideas. He uses the generalized Cowling theorem, and it has some interesting tectonic implications and then climate relationships. This is the external way. Most people are familiar with these types of changes. The induction energy, which many of you have touched on, is the mystical energy that we can't seem to put our fingers on. And we're going to show you how we think that works. But it's tied to deep water currents, creating magmas, earthquakes possibly, tied to solar changes in solar magnetism, mostly other forces from maybe outside the sun. A lot of it's tidal driven, which a lot of y'all discussed. The hydrodynamic dynamo. And he's going to discuss the atmospheric condenser, which is what climate basically is. It's where in the middle of the capacitor plates, you've got the ionosphere and the core, and the atmosphere is where all the interaction happens, the condenser. So we'll discuss these concepts. Basically, you got a magnet, core. Let's see, let me go ahead and get all this stuff up here. Permanent magnet, a moving coil, which everybody here is familiar with. Inside the Earth, permanent magnet, right here. The moving coil is the core, producing thermal currents from the magnetic field. Alright, so that's just general basics there. And the tidal loading, it creates a stress differentially on your lithosphere, your mantle, and your core. So you get a differential stresses which create a kind of a westward drift. This isn't talking plate tectonics, but the plate has similar ideas. And then the different energy levels within each one of these. With your higher energy levels in the core, in the mantle, it's kind of medium, and then the lithosphere is lower. He quantifies them here with your powers here, 10 to the 20, 18, and 10. But your asthenosphere, lithosphere boundary, your inner core, outer core boundary, and then your core mantle boundary at the outer core. So I'm not going to read all this to you, but you see this is what he was talking about a minute ago, the logarithmic energies associated with those 3 general layers in the Earth. And then he goes on to talk about how these layers aren't necessarily perfect. He talks about the Hamilton principle, variation principle, and the propagation of these, what he calls a sea urchin spike. It's a, let me see, he's got another, here we go. You got the loop, and here would be the spike right here, which is generated by the Hamilton's variation principle. And I'm not a mathematician. You guys probably understand the math better than I do. So it becomes a series of this emanating from the inner core, and outer core. There's your St. Elmo's fire. Created a sea urchin model, which resembles something like this. Most of y'all familiar with a sea urchin. You have a lot of spiny spikes coming out. So here's your inner core. You get the circulation in the fluid outer core, and you get these electropotential spikes that reach up to different density boundaries, and there's different discontinuities in the mantle. You get your deeper earthquakes, 800, 600 levels, kilometer levels, and then you get your spikes in the upper levels at the asthenosphere, lithosphere boundary. So there's a series of these spikes, and they cluster in these, like triple junctions within plate tectonics. So you get clusters of them in certain places, and they supply the energy for volcanoes. I believe he's got some more information up here. Probably along the spikes, supply geothermal flux and volcanism. Let's see if there's any tidbits up here, takeaways. Overwhelming endogenous energy source. He's basically saying it's mostly electrical. The nuclear decay is, I won't call it negligible, but it's probably not the main source of heat. And then he goes on to talk about a electric soldering iron mechanism by this propagation of the sea urchin. Comes up with this as an average number. It propagates slower at the lower boundaries, and as it rises, it increases in speed, likely because of the density change at the upper layer. So this is the Hamilton principle of the propagation of these things. If you notice, those are there's the same kind of magnitudes as kind of what they consider plate motion, centimeters per year type. That's interesting relationship. And then he compares it to several things, but a battery or leaky capacitor. You got your plates, the ionospheric plate, core plate, so you get this condenser effect between the plates. It charges up, it discharges, tied to variations of the solar wind. And there's your contracting expansion mechanism, okay? Let's reserve questions for later if possible, because I got a lot of slides. So you get this energy storage, you get a charging effect, contraction, discharging, expansion. That's the general concept. This happens on all different frequencies. Real high frequency oscillations tied to climate. You have a 40-day pattern tied to solar rotation, we believe. There's the Encino effect. There's the Pacific decadal oscillation, which is a 30-year trend. So you get these different expansion contractions effects. And as some of you noted before, it looks like a net expansion, which, in my opinion, I would agree with that. When we get to the atmospheric condenser, basically, he's showing, let me go ahead and advance this. I did something that just closed. There we go. I hit the negative button. That did something negative. Okay, so you got your solar wind dynamo, and he's talking about that as a current generator, as opposed to your. I did it again. Yeah, I'm just hitting the button below the tape down button. There we go. I'll that a little better. Current generator versus your tidal-driven geodynamo. The tidal effect is talking about a voltage generator. So you've got voltage and current. And then he has this little cartoon that's kind of humorous. The moon here is turning the lines in between the magnet, so it's like the lunar effect. You got that 9.1, 9.5 year effect of the related to global temperatures. And then you got your solar winds effects, which are up in here. So there's your currents and your voltages. So this is the mechanism, and he goes into a little bit more detail here about the same thing. It shows it can be positive or negative. Currents coming in or out of the ground. And then Same thing from here. So you're charging and discharging from the core. So it's a two-way street, this power. And it's really tied to the variation in the solar wind. And then he talks about the atmospheric condenser, your ionosphere with your positive charges mostly, and there's your amper or hoop or your sea urchin spike, and your relationships. He got a lot of detail here. I'm going to try not to read all this, but you see he's talking about steps of ionous charge, and it gets thicker. The GPS data is showing us the total electron content data show these this variation in thickness are actually pretty quick. And your sea urchin structure, I just mentioned, strikes and strokes, goes up and down, and then it ties into these terrestrial gamma flashes, Elton sprites. We'll show that in a second. So he's saying that the key to the problem is therefore the coupling between the positive charge in the ionosphere and the spikes in sea urchin. That's the part we need to figure out. So it's local, it's tied to real structure in the Earth and real structure in the ionosphere. So that's the key, is understanding the structure and how they're interrelated. And he goes, okay, this is basic electrical theory here, classical stuff. I'm not going to read this, but y'all can read it if you like. But there you go, dependence investigated on geometry, which is just what I was talking about, between the electrodes and where they're positioned on the planet, which I'm going to get into in my presentation. And then you have different kinds of effects, sparks, lightning, glows, luminous phenomena tied to earthquakes, earthquake lights, stuff like that. But all these effects are just different manifestations of this type of energy, but the energy is, the source is the same. Arc effect. So he's looking at the physical conditions where these ignition voltages. So this is just kind of a summary. And then how it's tied to the Earth itself. All right, so different spatial scales, the size of the sea urchin spikes are, they're tied to clusters and chains of sea urchin spikes, like the super swells, large igneous provinces. These are different scales, larger scales, mid-ocean ridges, nice long structures, changes in circulation. Now this is where it starts to transition down into, okay, the energy changes from electromagnetic to heat somewhere at one point, the joule heating. So you're getting hydrothermal venting. You get your geostrophic flow, normal geostrophic flow, but when you get this hydrothermal input, it destroys this vertical layering. It destroys the geostrophic flow somewhat. And you get these appearances of changes in circulation patterns as of that. They noticed this in the Adriatic during these events. Volcanoes with the double eye, you get the double magnetic signature. And then these lightning is a real tiny scale effect, and then this corona phenomenon, which I'm going to show you. I think he's got an example of that. Okay, here we go. These are, I should have kept going here. So this talks about some strange manifestations during 2003, this heating effect in Europe, hurricanes recently with the 2005 Katrina, etc. This is the western drift of the magnetic fields associated with that. Wildfire outbreaks are related in some cases, can be during coronal mass ejections. This is what you're talking about, the Adriatic conversion circulation, double eye pattern. Yeah, I should have gone ahead and looked through these. Okay. So there's your double eye pattern in the volcano. You guys can see that. And there's your St. Elmo fire. I think it's good. Yeah, corona effect, St. Elmo fire. So all of these effects are tied to the same concepts. They're just different scales. And then he gets into the Cowling theorem, a mathematician, I'm going to go through some math, so bear with me. Shows the history first, and I'm not going to go through all this, but this is kind of how it rolls out. Here's where he started publishing about this. This was a related idea. And then the takeaway is that he's using a generalized Cowling theorem that he casually discovered back in 2002. And with this idea, he goes on to explain. And I noticed in Bill Lucas's presentation a similar effect about this toroidal-poloidal relationships, unstable, stable. This is what he's talking about with the Cowling theorem. So this is your stable configuration between your magnetic field and your currents. Unstable. And he goes on to explain that a bit. One toroidal B, toroidal E. I'm not sure where the E is coming in. I think that's a J. But anyway, I'm going to go through this rather quickly. If you got more questions about this, we can talk later. But Giovanni's the one that really has got the map. So the Cowling dynamo, the stable configuration, is what he's using to talk about this propagation and atmospheric condenser effect. And he says the process is ubiquitous, and it explains observational evidence from galactic superclusters to the microscale, which is pretty much what Bill was discussing earlier. The jellyfish flames observed on ISS, I don't know if anybody's seen that video, but it's this little bubble that has this light that propagates it through it, and it looks like a jellyfish, but this idea explains that effect. Ball lightning, and then he gets into the experimental evidence. And basically from a drop of water that's placed right on this electrode, they evaporate it. It creates these luminous discharges. Ball lightning, I'll show you a couple examples. Like this. So there's one drop of water, very hot in the middle, almost cold on the outside. Let's see, discharge, generated by an water discharge. So this could be happening in our ocean basins. It could be happening in the lithosphere where we've got groundwater.
Can you explain that picture once more? What are we seeing there?
This is a lab-generated ball lightning or luminous glow discharge from a drop of water. And well, you have to go back to.
No, okay.
You have to go back to this. That's the experimental setup that they did this with. I can't really explain it that well. I mean, without.
Are the slides available on? Will they be available on the site?
Sure. Yeah.
I want to look at that. Thank you.
There'll be some. We're doing some follow-on papers after the conference. I think they're going to be published in the post-proceedings, or the proceedings. I can say that. So yeah, I just want to show you some of the effects. Blazing ball plasma. So these are real experiments that, and from a drop of water. It's just a drop of water on an electrode. They're generating these glows, demonstrating the Cowling, the generalized Cowling effect. This is what they're talking about, the temperatures. 1,000 degrees in the interior, almost cold at the surface. And then sparks, Tesla's looking stuff here. Dendritic patterns coming out instead of going in, so you get this like large-scale coronal effect versus the small St. Elmo's fire type. But that's just a matter of scale. It's the same principle. Domino effect. It's like each atom's like adding to the effect for each molecule. That's what he's showing here. You get your original ionization from some ion, and then your water molecules line up, and then they propagate the energy along the chain. And he's got a few other electric dipoles. That's what he's showing here. But basically he's stating that it's a propagation effect. The Cowling, generalized Cowling theorem is the energy propagates along these ionized particles, and it can happen like a chain reaction. It's kind of a runaway effect once it starts. It explains why H2O condensation occurs, and this is the idea of the atmospheric condenser cowling effect. It's explaining this atmospheric condenser. Let's see what else. Oh, here's where we talked about terrestrial gamma flashes and how it generates those from its runaway. Called it the runaway breakdown. These guys figured it out back in the day. You get the graph of where the energy actually breaks, the breakaway region occurs, and so this is where you get your propagation of the energy once this breakdown occurs. He believes this might be explaining some unexplained aircraft crashes, possibly. And then it's tied to this production of the sprites, L's, and the stuff going on in the upper atmosphere. It wasn't discovered that long ago. Alright. He's got a little bit more information here. Get back to the solar wind, the current generator, and then the tidal-driven geodynamo voltage regulator generator. And then this has some tectonic geodynamic implications how I'm doing on time. Rushing through it pretty quickly here. So the implications, now he has a little different idea. He's a big fan of Occam's razor. He likes that concept. So this is the very simplest concept. I think it kind of ignores the Coriolis effect a bit, but we're going to show the implications. The heating of the mantle, what he calls a super swell, which you're familiar with, like the East Pacific rise would be a super swell. Your spikes here in the sea urchin creating the heat for the super swell electrically. In other words, and then he's saying this is not a plate tectonic concept. You don't need plate tectonics. This doesn't explain plate tectonics. And he's saying that two supercells in the mantle, you get a gravity sliding towards the orogeny. To me, what's wrong with this picture is that this should be way up here. If you're looking at the examples I'm going to show you, he shows some, furze wrinkles. A lot of planets have this. Okay. So we got a couple examples. The geothermal flow and the gravity fields show how these supercells work. I'll go into that. First, the geothermal. See here the Southeast Indian Ridge, the Mid-Atlantic Ridge, the East Pacific Rise, and there's your orogeny, the Andes in between these two supercells. I'm sure there's some not as clear-cut evidence in Africa, but if you look at the gravity data, you see, and this is Grace data of basically Bogotazed, that's what I call it, but you're stripping away the topography. So you're seeing low gravity anomalies out here on the East Pacific Rise, the Mid-Atlantic Ridge, Southeast Indian Ridge, and there's your mountain building and the vents. So what he's saying, he calls it warm mud tectonics. He coined that phrase because he doesn't like paradigms, so he made up his own. But he's calling it your warm rises, creating some melt, and raises the superswell, slides down, creating an orogeny in the middle. Now, I have a little different interpretation. That's Occam's razor. That's the most simple type of explanation. But it just the Andes are so high compared to this is below sea level. So the picture he showed doesn't quite jive in my mind with how it works. And then we get into some climate anomalies, and he just has some examples talking about the internal and external way of climate. We see the sunlight, we see the cascading particles and lightning, but this is the hidden part that we're missing. And let's see what he's talking about here. So the external way, he you're talking about is planetary type effects from your sunlight, etc. The internal wave is more point-like, tied to these sea urchin spikes. Geoheating is very specific geographic locations or clustered locations. And here's your, he gets into 60% of the energy balance of geothermal energy is caused by this internal wave. It's quite a bit. That's his estimate. Okay, so I got through that one. I think I've got time to get into the next one. Okay, this is my introductory slide. Got a little nonprofit going on, the Institute for Advanced Studies in Climate Change, but also working with a business, Climate Stat. So this is showing how, if you look at this idea of the climate and look at these three specific frequencies. This is MGA is a 48-day frequency. Your NSNO is kind of variable, 3 to 7 year type frequency. This is an approximately 30-year effect, and they're all climate anomalies. We're going to get into that as we go. First, I want to show you the relationships in the Pacific Basin. Your NSNO effect is tied to a low pressure oscillation that's teleconnected to a high pressure oscillation over here. These are interesting structures. This is a triple junction in plate theory. I'll show you an example. It looks like a vortex structure if you look at the lithosphere closely, but I'll zoom into that. These are twin rotating microplates, they call them. Wonder what's causing them to rotate. Maybe mantle motion underneath. Again, you know, this is Giovanni's was warm mud tectonics, but if you had the Coriolis and flow, then you get more into a stream flow type process. It's very similar to the ocean and atmosphere. It is the same. It's just a different viscosity. You have somewhat of a teleconnection across your pathway for teleconnection. But you see this trend kind of comes up around here. This trend goes down, but they call this the Central Pacific Megatrend. And then, okay, the other relationship I want to show is this area is Lake Baikal, or Baikal, deepest continental rift lake in the world. And the Aleutians, or what they call that. Here is where in the atmosphere you have a low pressure system that sits over this area all the time. You have a high pressure, the Siberian high sits over this area all the time. So you have these atmospheric pressure connections that are teleconnected to these structures, I believe. So there's low pressure over the banda, high pressure over this region, high pressure over this region, low pressure over that. This has a approximately 30-year oscillation. This is tied to, they call it the North Pacific Oscillation. But there's also a sea surface temperature relationship tied to the same 30-year period. When it's a positive index, or what they call the Pacific Decadal Oscillation, you get a horseshoe-shaped sea surface temperature pattern in the Pacific. When it goes to a negative phase, you get an L shape. The Crucial extension is not near as strong. You get more of an L-shaped pattern. I'm sorry, the L shape is over here. So the U over on the west coast diminishes, or the anomalies seem to dissipate. So that's tied to the same pressure oscillations going on between these two, what they call the North Pacific Oscillation between these two high pressure and low pressure cells. So 30-year in the northern hemisphere, modulated tectonically, and then this El Nino Southern Oscillation effect, we believe, is modulated tectonically also between these structures. Now let me zoom in. Let's see. I think okay. This is kind of zooming into the banda, which I showed you over there, sitting north of Australia. You see the double comet. I think this is going to do this to me. Let's see if I can. It's going to do auto advance. I should turn that off. But you see this wing of the vortex? right here, a central eye. Looks very similar to a hurricane structure. You see that double comma symbol of a vortex in the lithosphere. And this, so there's Australia's down here. There's Sulawesi. Right, Papua New Guinea's over here. All right, and that's teleconnected. Now this is that's just bathymetry data of topography. This is synthetic. This is altimetry data that they call pseudogravity. But you see these ring-shaped structures in that data set. And this is Easter Island is in here, and the Juan Fernandez. They call them rotating microplates. I believe they're mantly driven. And the sea urchin spikes, although this is a very idealistic representation, I've just got one spike, it would actually be a cluster of spikes, like a dendritic lightning pattern coming up. And so all the volcanoes along the Indonesian island arc would be supplied electrically through this type of structure. The same thing on here, although this we believe is an upwelling mantle, and this is downwelling mantle. Some drift back to the west, but the heating is coming from below to probably these planetary scale structures. We believe sea urchin spikes, you have a direct connection to the core. And then you get this dendritic spread at the surface where it starts supplying electrical energy to the volcanoes. So these are idealistic mantle models, cartoon type models of what we think is driving these structures at the surface. And it's basically covered by a theory called surge tectonics. If you've ever heard of Meyerhoff, he's discussed this thoroughly. But the planetary scale vortexes, and here's your idealized model. I'll show you some real data that shows that it's a little more complicated than that, but it shows your direct connection to the core and vortex structures from sinking here in the Australian Antarctic discordance, which I also showed on that slide, but didn't go into detail about that. But basically the concept is, in plate theory, they would describe this sinking area on the AAD as a cold spot. So it sinks. Whereas surge theory, it's convergence of mantle on the ridge and the sinking. All right. But both these have sea urchin spikes associated with them, whether they're sinking or upwelling. And then that's just a reminder of what the sea urchin spikes that we discussed in Giovanni's presentation, the Hamilton principle, and then your clusters. Now we're going to get into a quick concept, and then I think we're getting away from using gravity instead of electromagnetics. But if you look at gravity data, Warburton and Goodkind back in the 70s, they were using superconducting gravity meters over in San Diego, where they build them, and they set up this monitor. And what you're seeing here is a monthly tidal effect of high frequency change. And this is the gravity data. And what they do is they take a high pass filter, they get rid of all the high frequency stuff, and they got a residual. And that residual, interestingly, matches very nicely the barometric pressure. So you got this barometric pressure effect in the atmosphere that's throwing a signal in your gravity meter. And once you get the high frequency gravity changes out, you can see it. All right. These are, okay, so 16 days. So you're looking at a month. I think a month correlates to one of these blips, all right? So these are each a month. So you're just filtering out this high frequency stuff, and you're seeing your gravity is actually monitoring your atmospheric pressure, okay? So what we're talking about is the reverse of that. You sea urchin spikes create a melt subsurface, an expansion. So you get a density change below, and that also can control your barometric pressure. That's what we're looking at with these teleconnected oscillation systems. And they quantify this effect. Let's see if my next one has that. I don't see the numbers here, but it's about 0.3 microgals per millibar. Very small. The pressure change across basin for an ENSNO or an El Nino, Southern Oscillation Pressure Oscillator, only about 6 millibars. But these are big, large areas of pressure, large cells. But this small changes in pressure, 6 millibars. typically to drive an aluminium. All right, so you do the quick math. That's about 2 microcals gravity change needed to affect that, but it's a large regional area. So it's a large effect, large area effect, but a very small change in density that could be the driver of this. And again, to remind you, the idealized idea, there's your banda, sea urchin spike, the planetary scale effects we believe tied to the core. There's your E-specific rise, Lake Baikal, I think that's the Alaskan. But that's just an artistic concept, whereas this is real data. John Quinn did a lot of spherical harmonic magnetic modeling analysis. You're looking at 30 to 65 degrees, harmonic degrees. And it's detecting, what he's detecting with this magnetic modeling is the salt flow remnants signatures. All right? These are the sea urchins. Now, a lot of these are ancient ones. They're frozen, that are no longer that active. Although they may be grounding conduits for lightning, and they may occasionally burst some electrical energy, but they're really the older frozen ones, whereas you got your Hawaiian hotspot out here, your Guaymas Basin Rift, so you have your active ones, over here in Asia, near the Philippines and such. Some of this stuff is offset from the surface because it's just modeling deeper. These are the depths you're modeling at, the colors that are associated. So you're talking, upper mantle in those cases, what we would consider upper mantle. So this is the real data that shows the present and past urchin spikes. According to Quinn, if you model this stuff up to about 720 degree harmonics, you can see where they come to the surface. He said his computer can't crunch numbers that big without overflowing, so he needs a supercomputer or something. But anyway, I think somebody's probably done that. I'm looking for that information. I don't currently have it. You can see right here in Florida, I just have this as an example. I know the geology of this area because I did some work over here. There's a Triassic rift that runs through the Gulf of Mexico, and it kind of trends upwards along the East Coast. So these are ancient Triassic related sea urchin spikes. They're tied to this ancient rifting, at least hypothetically. Okay, this is hypothesis. None of this is really proven. Now we're going to tie this effect to, how is this coupled to the planet? And most people are familiar with this classical ring concept. You got your connection to your ring currents here through the solar winds this way, but you also get your energy from the tail, plasma tail, where you get the reconnection, and it comes back, and the particles go in the radiation belts and then spiral back. So you're getting control of particles from that effect, as where velocities might be more tied to the solar winds directly. So the particle cascades in from the radiation belts, but the spinning of this ring, velocity possibly tied to solar winds at this level. And then just your basic induction concepts of how this energy is transferred to the planet. Okay, so it could be transferred, each individual sea urchin spike could be an antenna where this induction process can occur, but you can have a bigger scale effect if you start looking at the tectonic structure of the planet. Now, this is the ridge that rings Antarctica. It's not a perfect ring, you get some, goes up to the Pacific rise, and there's some, the Nazca plate over here by Chile. You get a connection there. Scotia Arc, a big eddy pattern here. The ridge then propagates through, and then as you hit, you see this goes under, gotta get oriented here. There's New Zealand, South Africa, Australia. So this goes through the Southeast Indian Ridge. It goes up here to a triple junction and then kind of comes back down. There's the AAD, the Australian Antarctic Discordance I mentioned earlier. So if you connect the dots here with this ridge structure, you kind of see this red thing. It flows and it goes all the way back to showing where most of the heat input, if you look at the map, is from the south. There's your AAD right here. Energy seems to propagate from that region up into the southeast Indian Ridge. And then East Pacific Rise is interesting. I believe the energy's coming in close to the Scotia Arc, but you've got some vortex structures here, one the triple junction here. So this energy's coming in at the south, I believe propagating northward predominantly. That doesn't mean there aren't sea urchin spikes other places where you're getting this induction process occurring. And okay, so now we're going to get into a discussion of the climate and how that's related to this curve is. Yeah, I got that automatic thing going on. I think once I back it up, it gets rid of it. So you have this is measurement on Earth. This is a 5-year running model of the magnetic field. Johnny Quinn used to do this for the Navy, so this is his model. And you notice not very much activity back here when the data was more sparse, but as you start to get the satellite data, you start getting more detail. So this curve might be a little bit misleading. There was probably quite a bit of inflection going on back here, but they just didn't see it because they didn't have the detailed data like we do with the satellites. But if you notice, this is when the magnetic field is increasing, and this is decreasing. Now, this is measured here on the planet, but this effect is driven by solar magnetism. So you're seeing an effect on Earth, but the sun is what's controlling this. He calls it Earth magnetic moment percent decay per century. So it's basically a discharge and a charging effect. Discharge, charging effect. Right here is where we're up here now. And this is, if you go through the literature and you look at the global cooling and warming trends, these curves.
What's the time scale? I can't make it up.
That's 1900, 2000, so it's a little over a century.
Okay, thank you.
All right, and I've underlain the Pacific Decadal Oscillation temperature index for the same. I kind of lined them up. So there's 1900. It's the beginning of that past century, and then there's 2000. And you see the PDO index is positive. That's a warming trend. The PDO is the largest temperature proxy on the planet. All right, so when you see this trend going up, the planet's warming. When you see this trend go down, well, it's the cooling cycle. And if you just look through the literature, you'll see the records indicate cooling and warming from a series of proxies, but this is the most dominant one. And it's just, like I said, it's a sea surface temperature anomaly in the Pacific. It goes from a horseshoe shape to a L-shaped. Changes like that. So the L shape is in the negative phase, and the U shape is in the positive phase. This is in the northern hemisphere. Look where I showed you the teleconnection between Siberia and Alaska. So there's a modulation effect between those vortex structures. The inflection points, these smaller curves or changes, are how the El Niños. So the little inflection points. So this is a change in the magnetic decay is what's going on here. That's what's causing the climate change. And if you look at that, that's about your 9.1 year cycle. That's that lunar cycle. Awesome. We're going to look at some Scafetta cycles that kind of show you how we think it's tied to orbital stuff. I want to get through some earthquake evidence here. And if this advances, I'll back it up. But this was an earthquake cluster that we believe signaled the beginning of the El Nino in 97, 98. You saw, this is Peru, coast of Peru. And if you zoom in, I'm looking at that feature right there is this trench. Okay? So what we're doing is we see two distinct clusters of earthquakes. And the earthquakes occurred over about 2-3 day periods. I mean, it was an intense cluster burst that lasted for about 3 days. You had some residuals later. But most of the effects were very rapid, very quick in time. And then about 6 months later, you have this sea surface temperature anomaly showed up. And it's interesting, you get two little dark spots that are distinct Now the earthquakes actually occurred right here at the junction of this Nazca plate and the trench. So the earthquakes are actually here, but the circulation in the Pacific is this way. It's got this gyre. So the currents run northward here, so you would expect sea surface temperature anomalies to be displaced a bit northward. What's interesting is you get one up on the shelf and one more down on the slope. And that's what you're seeing here, one up on the shelf and one more down on the slope. And then, okay, so these are graphs. I know it's kind of difficult to read this, but this is 96. The earthquakes happened about November 96, which was the beginning of a hail cycle, by the way. The joule energy is just a logarithmic spike. You can see this one wasn't big enough to cause it to little wiggle. But this is the energy input from these earthquakes, calculated in joules directly from the Richter values. And if you notice, okay, there's 96. About 6 months later, you begin to get this huge sea surface temperature anomaly. All right, and that went to 98. So this was the El Nino. You see it start right here in the trench. Now I know Noah and all those guys are saying it's this warm pool of water coming across from the Western Pacific that comes underneath somehow and then pops up, maybe with the circulation of the ocean or such. I think the heat signal first shows up right here if you look at the time series, and then it blows up to a peak that looks like that. This is the full-blown El Nino, and they define El Ninos with the pressure oscillation, but they also define it with this temperature anomaly in the eastern Pacific. And this is huge. This is the size area, about the size of Europe. It's about an 8-degree anomaly, so it's a lot of energy. But if you notice, there's this bifurcation right here. And it's interesting because the Picos Ridge comes out of Central America towards Galapagos, and the Carnegie Ridge comes out here towards Galapagos. And so you got these interconnected ridges that bifurcate. You got a sea surface temperature anomaly that bifurcates right above it. And simultaneously, up here in the Guaymas Basin Rift, which is a known geologic hotspot or sea urchin spike, you get another signal simultaneously. So this area is emitting heat, we believe, and it's it manifests at this point as a hydrothermal expansion or pushing out water on the ridges. So that's what we think is going on. You're getting this heat signature from the sea urchin spikes. That's describing the El Nino. And the pressure oscillations. Okay, so these pressure oscillations that describe those, that's what rearranges the jet stream pattern. So this effect not only makes these huge sea surface temperature patterns, but you get big mode changes in your jet streams, which is what climate change is. Now I want to show you one more thing about the earthquake data, and this was curious to me. I was looking at nines mostly. I went to a National Earthquake Center, and they have a table already for magnitude 8s and above. So I just grabbed it, and I chopped out a little bit above because it was too much. But right here, you see in 2004 was your Sumatra earthquake over in Indonesia. You didn't have a 9 since '64. So what's going on here? What was the big hiatus between that? Well, this is when I showed you that magnetic decay curve. During this period, this hiatus, you were discharging. The planet was discharging. As it's discharging, you don't build up the energy for the 9.0 earthquakes because you're constantly discharging energy on a net basis. But during the charging periods, once it reaches a threshold, then you start being able to have your 9.0 earthquakes again. So we're going to go through these. We're going to have some more of these probably till about 2035 or so. Expect a series of these 9s, and then they'll dissipate for about 30 years again. It's not that clear in the data before that. You see a couple 9s in here, but then before 1938, basically you don't see any 9s. So I can't explain that. But this is where the temperature trend changing here where this area is. So that was where your magnetic decay trends changed again, for about where this area is. So, you know, it's not clear that it operates, but it's just a hypothesis, okay? So that's what I think is going on with that. That's my opinion. And then we're going to talk about the sun a little bit. This is coronal mass ejection, but sunspots, etc. Actually, this coronal mass ejection occurred in 2003 around Halloween, right when all these wildfires broke out. And I'm not getting into that, but I'm just going to give it as an aside. You had all these wildfires break out in Southern California during this coronal mass ejection. So we believe the sea urchin spikes electrically emanated by induction a lot more energy, possibly pushing out methanes, and like superfire just ignites along the ground. That's the concept. I didn't get much traction on that when I made a proposal to USDA about it. All right, now we get into a little of this. Let's see, this is Phillips. Okay. Giovanni sent me this. I decided to put it in my presentation because he already had so much. But you see, the red one is our current sunspot cycle. But you see there's a huge variation when you look at 23 cycles. So the point of this slide is, though, what he's showing is that you have these huge variations, but then they taper off right here, and they look similar. Let's just read this. Every spot can be different, but the difference is more evident during the first half of the cycle, during the first 5.5 years, while the remaining parts appears like a smooth decay towards the next minimum. So this was work by Phillips. If you tie that to an idea about Scafada, he talks about internal forcing versus the mean field, external forcing versus the mean field, the internal forcing, which is what Giovanni's talking about, internal versus external way. You notice, okay, consider these were sunspot cycles. This is just kind of oscillators. This is just an experiment. I don't know the math behind the Kermoto model equation, but basically it relates to the same idea. If you got a bunch of cycles of different magnitude and they start, okay, so they start at different magnitudes, they quickly equalize to the mean field, the internal field. So if you're looking at Earth, we're looking at, so the internal magnetic field, the strength of that controls this first trend to the forcing. So you see these lines are parallel here. But then what happens over time is it smooths out and becomes more parallel to the external forcing. This is the planetary orbits, right? So the solar system effects smooth out. And that's what climate's doing. You get these climate oscillations, but they're not perfect cycles. So you're getting some magnitude injected of change in magnetism first. The mean field dampens that. And then the external oscillators take over and start to control the cycle. That's what it appears to me is going on. And then this is some more Scafada data just showing that your 20 and 60 year oscillations, which are tied to Jupiter and Saturn. So those are some of your oscillators that we're talking about. And we see that the 60 year would be that 30 year curve I showed you, the charging and discharging. The 30 years is half of the cycle. So you get the other 30 years. So for your 60 years oscillators, that's tied directly, and it works. It doesn't necessarily affect the Earth directly. The way it's affecting the Earth is by changing the strength of the sun's geomagnetic output, which reflects back to the Earth. So that's, the oscillators aren't, there may be some direct effect on the Earth, but the more effect is changing that center of mass of the solar system, which is changing the geomagnetic activity of the Earth. This is a little more Scafada data that shows this 9.1 year cycle tied to the moon. So he's looking at the he's looking at speeds, PS speed, what's PS? Power spectrum. Okay. So he's looking at these speeds and he's showing this moon cycle here, pretty dominant. I think he goes on to show that related to a global temperature trend. So your global temperature trends And I showed you how those El Ninos were tied to that periodicity on that decay chart. Alright, so you can see they correlate in a few places, not everywhere. There's your moon period. Anyway, these were just to show you some of the modes. I didn't want to go into too much detail on this, but and then this is your center mass of the solar system in Earth radii. So you see how much over time the center of the solar system is shifting full Earth radii, full solar radii easily. And this effect is what's tweaking the geomagnetism of the sun, controlling your sunspot activities possibly, and that's the effects that are tied to the intensity of the climate change. Okay. And then we get into a higher frequency modulation. Some of y'all discussed rotation of the sun. The pole of the sun rotate at a different speed in the equatorial region because it's plasma. The poles, which are where the magnetic field of the sun is mostly tied to, are rotating in a 36-day rotation, approximately. So the Earth, right in here somewhere, feels this sweep. All right, so the sun rotates 36 days, but now the Earth is moved in that 36 days, some period. So it takes this sweep 4 more days to catch up to it. If you do the math, you'll see that. So the Earth experienced the polar rotation of the sun and the strongest magnetic component in a 40-day period. Well, there's an interesting climate anomaly associated with this 40-day period called the Madden-Julian oscillation. And I'm going to show you that in a minute. But what you're looking at is each side of this wave. One side is a polarity. That's where your polarity changes occur. The amplitude of the wave is related to the magnitude of the field change from the sweep. So you're getting this magnetic change in polarity and field strength every 40 days. And there's the boundaries on the sun that are causing the sweep. So you got a negative and positive charge right on the surface of the sun. These are your hail boundaries. So these are where these Birkeland currents are emanating and sweeping, and that's your polarity. And it varies. This is the strength of this varies a lot, significantly. I don't have any charts to show how much, but there's huge changes in that. So what I want to show is there a relationship between this meridional sweep, the Madden-Julian oscillation, which is a real high-frequency El Nino is the way to think of it. It's the same kind of effect as an El Nino, it's just a 40-day effect. But it's the same temperature, precipitation anomaly that slips across the Indian Ocean and tied to the Indian monsoons, by the way. There's also another interesting thing going on. This is why I believe there's a polarity change associated with it. There's a 40-day power spectra in the earthquakes that correlates to this same period, and it's a north-south oscillation, to the north, to the south. That's why I think this polarity change is controlling that. So, are these things related? Can't prove it, but it's mighty suspect. So here's what happens when your Madden-Julian moves through. You get your sea surface temperature moves through. There's a precipitation anomaly associated with this. The atmospheric condenser, right? And this thing moves all the way across. Starts over here near Africa generally, and it moves across all the way across the Pacific. So it moves across the Indian and Pacific Ocean. You have big jet stream pattern changes associated with that. Big precipitation anomalies associated with that. The polar vortex could be tied to that we get up here. So, are these things related? Well, we can't necessarily prove it, but these sea urchin spikes are controlling this, tied to this solar sweep. It could be the mechanism for not only controlling this high frequency of 40-day oscillation, the ENSNO, the PDO, all these big global climate changes are directly tied to this effect, we think. All right, so this gets into the earthquake analysis that this fellow did, a guy named Kirsten Meacher. He's at Florida State, down in Tallahassee. I was interested in hurricane, how that affects, especially after Katrina wiped me out down on the Gulf Coast. But I went by and talked with him and showed him some of these concepts about earthquakes or how they're tied to El Niños and such. And he got interested. And he's a meteorologist. He's looking at earthquakes, so that gives you an idea. He took an interest in this. And what he found, he looked at earthquakes all around the Pacific Basin. But what he found was on the western rim, in these stippled areas, yeah, that's where he found this north-south oscillation thing. So he didn't find it anywhere else except this. And there might be a reason for that. This is the data that he used to show this. It's a bit technical. You almost have to read the paper to understand the analysis, how it works. But he's basically showing these changes in swings with these elliptical diagrams. It's a statistical analysis, so it's a bit complex. But that's what when you see the pendulum oscillation earthquake frequencies swing north and south along the western rim of these periods. It's 40-day power spectrum. I can get you the paper if you're interested. So there's back to that relationship. I think this might be my last slide, so we're doing good on time. All right, we got a little bit of time now. Let's keep
Not
going.
really. Yeah.
Just keep going. Okay. So we're looking at, now we got the AAD down here, Australian Antarctic Discordance. We got this stream around Antarctica, which I was showing you. So this huge transformer ring, if you got a plasma ring up in space and you got a ring in the tectonics, it's a natural transformer. So you get this transformer effect mostly from the South Pole. It doesn't mean there's not similar effects in the North Pole, but they're just, here's your geostream going along the northern Pacific Rim. It doesn't go nicely around the pole, so you got this, and then you got the Gackel Ridge over there, and the Atlantic goes right across the North Pole, more like a theta structure. So the coupling is better in the South Pole for that reason. But the energy seems to be mostly along this western Pacific Rim. And so you have, if you look at, you have three vortexes aligned: AAD, Banda, and Lake Backward. So three huge antenna, or sea urchin spikes, we call them, coupled to this ring going around Antarctica. I'm surprised you don't see some effect over here in the East Pacific Rise, but you didn't pick it up. So this seems to be where the dominant, what's called the dominant effect. Your Madden-Julian oscillation emanates from this region. Actually starts in Africa over there and then kind of goes all the way across, but this is the central region. Your Insno effect is tied to the Banda and the East Pacific Rise, big pressure oscillation across that basin. And then your PDO, which is your lower frequency, your 30-year frequency, tied to this structure. So that's why I believe it's all three short-term climate frequencies, Madden-Julian, Insno, and the Pacific Cadal, all have links to this Western Pacific Rim. So those are all interesting tidbits that I'm throwing out there at you. Don't want to make too many conclusions, but I believe that could be the end of my slides. So, we can talk about anything you like, but we got time.
We don't have time.
Okay.
I guess this is go for lunch and come back in an hour.